Hello guys, welcome to IBDepressed, where we post physics higher level revision videos for students taking the IB diploma. For today's lesson, we will go through the first unit, measurements and uncertainties. Now, first of all, what are measurements? Well, it can be defined as the size and or magnitude of something. For example, if we scroll down, the height of a rat is approximately 5 foot 6 inches or 168 centimeters. Now, we often evaluate measurements in terms of their precision and accuracy. What's the difference, you ask? Well, accuracy is how close a measurement is to the real value of what is being measured. For example, if you measure the height of a rat and find him to be 215 centimeters tall, this is obviously wrong. The measurement is thus inaccurate. Inaccurate measurements are often created by some error in the process of measurement that result in a shift in your values. For example, you might not have started at exactly 0 centimeters when measuring the height of the rat, but rather 47 centimeters on the ruler. This is a form of error known as systematic error, where all your measurements are inaccurate. Solving this systematic error should fix your inaccuracy. Now, accuracy can also be how close the value you've measured is to the actual value. So let's say you measured the height of the rat to be 169 centimeters. You measure that 3 times and all 3 times you got 169 centimeters. Your values would then be accurate, since they are very close to the actual value of 168 centimeters. Precision, on the other hand, is how close all your measured values are to each other. For example, if you measure the height of the rat 15 times and all your values show that he is 215 centimeters, your measurement is still precise as all your measured values are close to each other. In this case, we say that your measurements have a little random error. Your measurements all give the same answer. Now, we can also illustrate this concept using 2 targets. So I've drawn 2 targets here. On them, I've drawn 3 green dots illustrating where the arrow has landed. You can sort of think of your aim as the measurement. On the left-hand side, we see that since they're close to the bullseye, your measurement is accurate. And since they are close to each other, they are also precise. However, on the right-hand side, they are far away from the bullseye, but close to each other. Therefore, this measurement is precise, but not accurate. The idea of precision leads quite well into the idea of significant figures. For example, if the rat is said to be approximately 170 centimeters, this value is perhaps not as precise as we would like, but it is accurate to 2 significant figures. 168 centimeters, however, would be 3 significant figures. Now, what counts as a significant figure? It can be any non-zero figure, such as 2. It can also be a 0 in between 2 non-zero figures, for example, 606. It can also be trailing zeros after decimals, for example, 0.0600, which would be 3 significant figures. A final non-decimal 0 might also be significant, but we do not know. It can vary or be dependent on the context of the question. Let's take 170 centimeters as an example. In this form, we could have either 2 or 3 significant figures, depending on if the final 0 is significant. Meaning, have we rounded up, or was the answer measured to be exactly 170 centimeters? To solve this issue, we have scientific notation, which is written in the form a times 10 to the power of x, where a is some real number between 1 and 9, including, and x is the number of times you have to divide the number by 10 to make it between 0 and 10. For example, 168 centimeters in scientific notation can be written as 1.68 times 10 to the power of 2 centimeters. 170 centimeters can be written as 1.7 times 10 to the power of 2 or 1.70 times 10 to the power of 2, depending on how many significant figures. So, in this case, 1.7 times 10 to the power of 2 would be to 2 significant figures, and 1.70 would be to 3 significant figures. So now you may be able to tell how the number of significant figures of a value is dependent on the context of the question or the nature of the measurement given. Now, let's just have a short quiz to how many significant figures is this value? 0.00000006. Now, I've drawn it for you to make it easier. Well, in order to be able to solve this problem, we have to first realize that this is a decimal value. It has no trailing zeros, and there is only one figure that is non-zero. Therefore, this value has to be to one significant figure. If we convert this into scientific notation, we get 6 times 10 to the power of, you have to count the number of decimal places to figure out what power it is to. That is 1, 2, 3, 4, 5, 6, 7, and 8. So in scientific notation, this value becomes 6 times 10 to the power of -8. And we can also see here that this is to one significant figure because you exclude the 10 to the power of -8. Moving on, let's try 9.0030. Okay, so we can see that we have two non-zero figures. There are 2 zeros in between the 9 and the 3, and there's also a trailing 0. Therefore, you just count the number of figures to get the number of significant figures, because all the values here have to be significant. 9, 0, 0, 3, and 0, they're all significant. Therefore, it is 5 significant figures. Moving on, this will be a more ambiguous number, 6,000. In order to understand why this is ambiguous and cannot be determined, let's try and convert it to scientific notation. Well, one form could be 6 times 10 to the power 3, but it could also be 6.0 times 10 to the power 3, or 6.00 times 10 to the power 3, or even 6.000 times 10 to the power 3. So, because we do not know the nature of the value, we cannot determine how many significant figures it is. Was it measured to be exactly 6,000? Was it rounded up? We simply do not know, and therefore it is impossible to determine. If you were given the value in scientific notation as, for example, 6.00 times 10 to the power 3, then you would say that the value is to 3 significant figures. However, it's dependent on the context of the question, again. Now, moving on, uncertainties are a way of accounting for errors in your experiment. They're used in every lab report or science extended essay or all your sciences in general, so they are very, very important. To give an example, let's say we have a measurement like 10.0. Because we do not know whether this number is accurate or exactly what the measurement is, we use uncertainties to account for this. So let's give an example. 10.0 plus minus 0.1 centimeters. Now here 10.0 is the measured value, and this weird symbol here just means that 0.1 is either added to or subtracted by the preceding value. So, essentially, what the uncertainty is telling us is that the actual value lies between 10.1 or 9.9 centimeters, thus accounting for any errors in your experiment. Now, here we have a typical IB problem that you might stumble on one of your exams. Here, the question says, the length of a rod is measured using part of a meter rule that is graduated in millimeters, as shown below. Now, based on the image they've given us, we can see that both the ends of the ruler have been broken off, and the object is not measured from 0. Now, to find out the actual length of the object, we first subtract 8, the largest value, by 3, the smallest value, to get 5 centimeters. Now, usually, with analog measurements, we take the uncertainty to be 1/2 the small scale division which normally would be 0.05 centimeters. But since the endpoints are broken off and the length of the object isn't measured from 0, we have to take into account the uncertainty for 3 centimeters and 8 centimeters. Now, when we subtract 8 minus 3, we have to add their uncertainties. Now, we know that the value of 8 centimeters has an uncertainty of plus minus 0.05, and the value of 3 centimeters had an uncertainty of plus minus 0.05. Therefore, when we subtract the value to get 5 centimeters, we have to add their uncertainties in order to find the uncertainty of the measurement. Therefore, the uncertainty has to be 0.1 centimeters. However, this still leaves two answer options. Is the value of the measurement 5 or 5.0 centimeters? Well, usually we want the value to be to the same number of decimal places as the uncertainty. So therefore, the answer has to be 5.0 plus minus 0.1 centimeters, meaning that the answer is C. Now, for digital measurements, the uncertainty is 1 unit of the smallest scale division. So, for example, let's say you have a digital thermometer. Let's just draw a digital thermometer, which gives you a reading of 12 kelvins with no decimal places. Therefore, 1 unit of the smallest scale division would be 1 Kelvin, and the uncertainty of your value measured would be 12 plus minus 1 Kelvin. Another way to find uncertainties is experimentally. If you do 3 experiments and find heights to be 168, 169, and 170, where all have plus minus 1 centimeters in uncertainty, you can find an average value. However, you also have to consider all these numbers when creating uncertainties. To find the uncertainty of an average, you do the maximum measurement plus the uncertainty minus the minimum measurement minus the uncertainty, and you divide all that by 2. So, if we use the above example, we start by taking 170 centimeters and adding 1 centimeters, which is the uncertainty, and subtracting that by the smallest measured value, which is 168, subtracted by the uncertainty, and this now becomes 171 centimeters minus 167 divided by 2. When you subtract it, you get 4 divided by 2, and therefore the uncertainty has to be plus minus 2 centimeters. This value is also referred to as the absolute uncertainty and is commonly referenced in general notation as delta x. Whenever you add or subtract two values, you just add their absolute uncertainty of the original numbers. Now, the relative uncertainty is defined as the absolute uncertainty, or in scientific notation, delta x, over the measured value. If the question then asks what is the absolute uncertainty of the measured value, you take the relative uncertainty, which is delta x, divided by 100, times the measured value. With multiplication and division, you add the relative uncertainty of the original numbers to find the relative uncertainty of the value. Furthermore, whenever you raise a number with uncertainty to a power of n, the relative uncertainty of the result is n times the relative uncertainty of the original number. This also applies whenever you're taking the square root or the cube root or any n root of the value, because n just becomes, for example, with square root, 1/2 or cube root, 1/3. This concludes our lesson for today. We hope you enjoyed and found it useful. Thank you for today. You are free to go.